We've arrived at section 5.5, where we're going to talk about vector space isomorphisms. And we're not going to cover this section in any great depth, but there are some concepts here that are very useful to know about. So before we start to talk specifically about maps between vector spaces, let's just review some properties of general functions. So let V and W be two sets, not necessarily vector spaces, just on this slide, and let F be a function. Then if we assume that F is a function that is one-to-one and it's onto. So remember how this works. So you have V, you have W, and then you have the map F. And one-to-one means that every point y is the image of just one point x in V. That's what one-to-one means. And onto means that every point y in W is the image of something. So now if a function is both one-to-one and onto, then if we, let's go back and redo this, suppose we fix any point y in W. Then because F is onto, so 2 implies that there exists an x in V such that f of x is equal to y, and 1 implies that there is no other point. X is the only point. So what this means is that we can define the inverse of f. So this means that the map g of y equal to x is well defined, and g is the inverse of f. We often write it like so. And what this means is that g of f of x is equal to x for all x in V, and f of g of y is equal to y for all y in W. So really, when a map is one-to-one and onto, it means that there's a coupling. Every point in V is uniquely coupled to one specific point in W through F. And F takes you in that direction, and then G takes you in that direction. So now let's add some vector space structures to the discussion. So suppose that V and W are vector spaces now. So now we do linear algebra. And then let L be a map that takes you from V to W. And this map is a vector space isomorphism if it is linear and it's invertible, which we typically express as saying that it's one-to-one and onto. And now the interesting thing is that if you assume these two things, then it turns out that the inverse is automatically a linear map. Then L inverse is linear. Okay, so whenever these two facts hold, if a map is linear on the one hand and it's one-to-one and onto on the other, then so you always know that one-to-one and onto, so these two facts mean invertible. So L inverse exists, and then you can show specifically in the case of vector spaces that the inverse is necessarily a linear map. And there's a close connection between vector space isomorphisms and invertible matrices. So to make this clear, let's introduce two bases. Let B be a basis for V, and let C be a basis for W, and then let A be the matrix of L with respect to the basis B and C. Then L is an isomorphism if and only if A is an invertible matrix. So this in particular implies that V and W have to have the same dimension, right? Because for A to be invertible, it needs to be square. And you can also show that the map, the matrix for L inverse with respect to, so now you go in the other direction, so this is with respect to the basis C and B, is A inverse. That is probably not very surprising, but it turns out to work exactly the way you would hope. Now suppose that L is a vector space isomorphism between two vector spaces. Then the important property here that an isomorphism has is that it preserves a lot of properties, a lot of linear algebraic properties. So a lot of the vector space structure of V gets carried over right away to W. So let's state some of these facts. So for instance, if, say, V prime is a subspace of dimension K in V, then if you map V prime over to W, then you get a subspace of W that has dimension precisely K. So the fact that L of V prime is a subspace in W, that follows only from the linearity only. That's enough. We saw that in an earlier lecture, that as long as L is linear and V prime is a subspace, L of V prime is necessarily a subspace. But the interesting thing here is that the dimension is preserved. Now, if you have a set of linearly independent vectors in V, then L maps them to a set of linearly independent vectors in W. So if Vj is a linearly independent set in V, then the images of these vectors forms a linearly independent set in W. We can do this for a spanning set. If Vj is a spanning set, for a subspace V prime of V, then L of Vj, the images of these guys, is a spanning set for L of V prime. If you have a basis in V, then the image of these vectors form a basis for W. Okay, so in other words, a vector space isomorphism, it preserves a linearly independent set, it preserves the property of being a spanning set, and therefore it preserves the property of being a basis. So we can talk about isomorphisms. So we've defined it as a property of a linear map. Next, let's talk about it as a property of how vector spaces can relate to one another. So let V and W be two vector spaces. Then if there exists an isomorphism from V to W, then we say that these vector spaces are isomorphic, which we write like this. So it's the sign equal to with a twiddle on top. That means that the two vector spaces are isomorphic. And as we've already seen, if two vector spaces are isomorphic, then in particular means that they have the same dimension. And in fact, you can make a much stronger statement, and this is an important result. This is really the main result in this section, which is that if you have a finite dimensional vector space and say its dimension is n, then that vector space is isomorphic to Rn. So basically, in some sense, every n-dimensional vector space is really just Rn. It might be disguised slightly, as in, say, the space of cubic polynomials. That is, so what we've seen many times is that it really behaves just like R4. They're in a strong sense the same vector space. And the vector space isomorphism in this case is simply the coordinate map that's given by any basis. So if you fix a basis B for V, then the coordinatization map that maps a vector x in V to its vector of coordinates is an isomorphism. From V to Rn. Right, so we saw this so I mentioned the set of cubic polynomials, and then if you just introduce a basis, for instance, the standard basis like this, then any polynomial of degree 3 or less gets identified directly with a vector in R4. And you can do addition and subtraction and check for linear independence and all these things. You can do it either on the polynomial side or on the vector side. They're really, in a strong sense, identical. So as a corollary of this theorem, you also know that if V and W have the same, and here I'm assuming finite dimension, then they are necessarily isomorphic, because they're both isomorphic to Rn. Right. So as a slight caveat is that in this course we're talking only about real vector spaces. So let's write this out. So we discuss real vector spaces only. So you can certainly have complex valued vector spaces. You can have vector spaces over all sorts of different algebraic objects. You can have them be over discrete numbers, over the set 0, 1, and so on. So, but all that is outside of the scope of this course.